Two-sided marketplaces are a great way to resolve supply and demand inefficiencies. There is such high demand for great programmers, but there is only a limited supply. So why would it make sense for a great developer to use a terrible tool like a job search engine? That's why I love Hired.com. Developers can sign up at Hired.com/softwareengineeringdaily and be connected with 5 great job opportunities at companies like Stripe, Uber, and Facebook. If you're a developer, you shouldn't settle for a mediocre job. And I know this from personal experience. It will stunt your career growth. Hired will give you a $2,000 bonus if you find a job. And if you go to hired.com/softwareengineeringdaily, you will get an additional $2,000. It costs you nothing to try it out, and it's a fun process. I urge you to try it out. Distributed systems are a complex topic. There's abundant research about it, but sometimes it's hard for a beginner to know where to start. My guest Alvaro Videla is a core developer for RabbitMQ and a distributed systems blogger, and he joins us to explain some of the core concepts of distributed systems. Alvaro, welcome to Software Engineering Daily.
Hello, Jeff, and thank you for having me.
So you wrote a blog post recently called What We Talk About When We Talk About Distributed Systems. Why did you write this?
So I've been following the distributed systems community, let's say, since quite a while, mostly because I've been programming in Erlang since 2009, probably, or maybe earlier. And it's a community where there are many distributed system engineers. I remember my first conference in London about Erlang. And there were the original developers from Basho, for example, the one that made React. Mm-hmm. And they were the guys that built the Akamai CDN. So for me, coming like a total beginner to this conference was already pretty amazing. And I was following them. I remember where they introduced React and they have all this eventual consistency and whatnot. So since then, I kind of started following this community. You probably know Kyle Kingsbury, Afir, or he writes about Jepsen and tests many systems like RabbitMQ, Elasticsearch, and so on.
Yeah, he brutally tests them.
Exactly, yes. And it's just by following his stuff, people he retweets. I also know many other engineers like Ines Sombra from Fastly or Katie from Twitter, and they're always posting the blogs and whatnot. So I wanted to know more.
Yeah, we interviewed her.
Cool. I mean, Katie or Ines?
Did you say Katie? Katie McCaffrey? Is that who you're referring?
Yeah, exactly,
Katie.
Yeah. So I wanted to know more because I found this a really interesting topic. I think it's something in particular that, for example, as a RabbitMQ engineer, I should, of course, know. I mean, there are many areas that belong to what is to develop a broker. Many times you are just, let's say, working on the pub/sub system and not necessarily on the replication side or whatever. But still, I think it's something worth knowing. But the problem was where to start. Like, I started seeing there are books like here I'm seeing my library behind my monitor. And for example, I found a book from MIT Publishing that says the title is Programming Distributed Computing Systems. Cool. I say, okay, I can buy this book, learn a bit. When I get the book, it was actually about programming languages for different kind of abstractions on distributed systems. Like they introduced the lambda calculus, then the pi calculus, then the actor model, which I knew from Erlang kinda, and the I/O automata, which is the one that Nancy Lynch uses in her books, and so on. But the book was not about programming distributed systems, if you know what I mean. It was just, these are these models here, but they are not really going to help you at all. If you want to, let's say, build a real system like Rabbit or React or whatever. So I was always wondering, okay, now there is this other book, which, let me read the title, Distributed Algorithms for Message Passing Systems. Okay, I work in Erlang, distributed systems, message passing, let's buy this book. And the book has lots of algorithms. It talks about vector clocks, sequential consistency, atomicity, whatnot. But at the end of the book, nearly like the last page, the author mentions that the whole book doesn't consider faulty cases. So you have a full book of algorithms about the happy path, which is really cool for learning, but you end up again with some knowledge that doesn't really apply on the...
Yeah, kind of ironic, because distributed systems is all about faults.
Exactly, but what is really important to not dismiss this kind of research is that they are giving you the fundamentals.
Right.
And so I kept learning by the same author. He recommends some other books. I bought one, for example. Let me, again, read the title. For example, one book here says fault-tolerant agreement in synchronous message passing systems. Okay? Now there is fault tolerance, so probably there are faults, and these algorithms tolerate those faults. That's cool. Then the thing says agreement, that's consensus. Yeah, I hear that word a lot, so probably I need to learn what consensus is, let's say. In synchronous message passing systems, Erlang fits the bill, and then synchronous. What does synchronous and asynchronous means? I learned that it's completely different from what you will get, let's say, from the Node.js community, to name one.
So what you're getting at is that there's all these concepts, all these different topics, and it's really hard to know where to begin. It's really hard to draw a path from point A to point B, where point A is no knowledge about distributed systems, and point B is enough knowledge to get things done, to have conversations, to be effective. I think this is a fairly common problem among programmers who want to get into distributed systems. So, you know, this post this really good blog post you had that I'll put in the show notes, it begins with, a quote. Well, the talk that you gave that goes along with this blog post, it begins with a quote from Leslie Lamport, who is commonly referred to as the father of distributed systems.
Yep.
And the quote is, "A distributed system is one in which the failure of a computer you did not even know existed can render your own computer unusable." And I think this is such an interesting quote, because many programmers who are getting involved in distributed systems for the first time, they're like, holy smokes, I'm not even used to programming beyond a single machine. And now I have to start thinking about multiple machines, of which one or more may fail. So why did you begin your talk with this quote?
Mostly because it's kind of the canonical definition of distributed systems. It gives you an idea of the problem where you're getting at, that you're getting into, but at the same time, what does it say? I mean, I'm not disrespecting Leslie Lamport. I think, who am I to judge his research? But I'm saying that, yeah, everybody, like, I've been to many conferences about Erlang, for example, and many people just put this quote out there. And, okay, what do I do with that? For me, it's like, okay, yeah, I get it. There are all these problems that can happen. Computers can crash. Cool, but what does it mean to me?
Okay.
I'm somebody that want to get it started, and I should see this quote. Yes, I get it.
So getting from that quote to actual applications, that's the root of the title, where you say, what are we actually talking about when we talk about distributed systems? I get that there is this quote that's an abstraction of all these different things we could be talking about, but what are we actually talking about?
Exactly. And for example, there is a great blog post. I don't remember the name of the author, but it's quoted in my blog post about the FLP impossibility. The Fisher, Lynch, Patterson, I think, are the authors. That there is no consensus in a synchronous system with one faulty process, basically. Mm-hmm. Anyway, people, you will learn or read online that people will tell you, read about FLP. You should read about Paxos. You should know about this and that. This happened to me, for example, when I met an engineer of a very big company in a conference in Russia, and I was implementing the whole PubSub. I mean, not the whole PubSub system of Rabbit, but I was doing some thing that had more to do with algorithm related to string matching, pattern matching, completely unrelated to distributed systems, but which will make RabbitMQ deliver message pretty fast. But this person told me, you should know this, you should know that, you should. Okay, I should, maybe, yeah, but why should I? That's my question, And if you tell me you must learn about FLP, okay, but what does it even mean, FLP? And as I was saying before, you read the word asynchronous, and asynchronicity in distributed systems has nothing to do with what you will understand, for example, from Node.js, which is like a common example today of asynchronous programming, where you have like callbacks when you send some request, and instead of waiting for the request, you keep doing things, and at some point you get the data back from the request, right? That's what I will understand versus a synchronous system. When you do the request, you block. When you get the data back, you keep moving, right? Those concepts are totally unrelated to the meaning these two words have in distributed systems. So how can you understand FLP, which is a result that applies to asynchronous systems, when you don't know what the word asynchronous means?
So we'll get into these different terms, asynchronicity, FLP. I do want to discuss these things, but I want to give a little more of a motivation for why people should care. So there's a quote from Mark Cabbage where he says, "Face it, you are building a distributed system." Is everyone building a distributed system these days?
Look, I was actually going to get there because recently I got the privilege of seeing an early draft of thesis from Peter Alvaro, a researcher in distributed systems. And one quote from his paper says, the relatively recent accessibility of large-scale computing resources, for example, the public cloud, and proliferation of reusable data management components like NoSQL stores, data processing frameworks, and so on, have created a crisis. All programmers must learn to be distributed programmers. I think that's, for when I read that from this paper, was like hit me in my head, let's say. And people say, like, for example, if you do web development, you need to synchronize the cache in your browser to whatever database you have in the back. That is a distributed system problem already. You need to even replicate MySQL and see, just to name one data store, and make sure consistency is there, or what are the problems that will happen if you do master replication, or I don't know, whatever. There will be all these kind of problems all the time in programming, whether we want to admit it or not. Whether we are really going to implement some consensus algorithms or leave this problem to somebody else, to understand the possibilities and impossibilities, I think are related to understanding distributed systems. That we have all these, like this paper says, all these NoSQL stores, queues, some queues offering one guarantees versus others. Like I know competitors of RabbitMQ, competitors to give them a name, other queues in the space, that they claim to be super fast or non-centralized, but then they send duplicates to users. So as a user, you need to understand, okay, cool, there is no central server, there is no single point of failure, let's say, but at the same time, what guarantees are going out of the window because I choose to not have a master, for example. And even having a master, you can do some high availability architecture decisions to not have a single point of failure anyway. But the point is, you need to understand what you are getting into. Like, every vendor will advertise that their system is better. Like RabbitMQ will say we are better, Kafka will say they are better, NSQ will say they are better. Everybody will claim to be better. Okay, but that's nice. I understand you need to sell your thing, but what am I gaining as a user, and what am I sacrificing as a user by choosing your product?
And if you opt out and say, I'm not a distributed systems programmer, there's no way you can audit which one of these is the best solution.
It will be hard, but at the same time, I think you don't know which things will not be guaranteed at all by certain system because of the architectural decisions of that particular system. It's for example, people wanted sharding in RabbitMQ. I implemented sharding like a plugin for doing that. but I want to also now, let's say, it's faster. We don't need to lock on a single CPU, whatever. But we lost ordering of messages. You know what I mean?
Right.
And Kafka, for example, offer the same. And yeah, we are super fast. But then where is the order of messages in the stream that I may need for this particular use case that my application company needs? So it's very.
This is so interesting because I did an interview with Neha Narketa from Kafka recently, and there's certain things where like I don't do a lot of programming in distributed. Well, I haven't written a single line of code that interacts with the Kafka application. So because I'm not an expert in that, there are certain things where I'm having a conversation with her and I can't say what is the problem with X in Kafka because I don't understand the system well enough. So perhaps and so that prevents me from really getting into a dissection of, like, for example, how Kafka would compare to RabbitMQ. So I think the motivation at this point for needing to know distributed systems concepts, everybody needs to know some distributed systems concepts, whether it's early in their programming career or eventually. So I'd really like to get into discussing some of these core concepts because you go over these in your blog post, you really enumerate them, and it felt a lot like the distributed systems class I took in college. So the first concept that I want to discuss is timing models. There are several timing models in distributed systems, and you mentioned some of these, and I'd like to go through these. We have the synchronous model, the asynchronous model, and the semi-synchronous model. Could you define each of these?
So in the synchronous model, it's that everything that happens in the system can be timed. So you know exactly how long it takes for a message to reach another node. I mean, just to backtrack a bit, if we are talking about distributed system, we talk about different entities, which are nodes, processors, however you want to call them, that are trying to cooperate to reach a common task. It's not the same as parallel programming, where many nodes are doing something in parallel that not necessarily contribute to the final goal, let's say. You can have many processors resizing images, let's say, in parallel. That's not per se what the literature will consider to be a distributed system, to be clear. In a distributed system, these nodes are all working together to reach some solution. And because of that, they need to share data. They need to arrive at some kind of common state in the system, but they don't know what's happening on the other nodes. That's just to be clear what we are talking about. And in a synchronous model, we know exactly how long it takes for a message to reach the other node, how long a node takes to execute one step of the algorithm. And usually these steps are taken in rounds when we talk about the synchronous model. So, for example, an advantage here would be that I know the network has a latency of, let's say, 1 second for a message to reach the other node. The other node has 1 second to process the step, whatever that is, and 1 second to reply back. If after 3 seconds I don't get a reply, I know it will never arrive. Mm-hmm. I know for sure that the other node crashed, is down, the network is broken, whatever. But I know there is a problem in the system, and I can be sure there is a problem. Because of that, there are many algorithms, let's say, that can be implemented. Like we could talk later about this, but like a perfect failure detector. Because for what I just explained, you can perfectly know when some process has failed. The problem with this model is that it doesn't really resemble reality, except for probably a real-time system, like, let's say, the components in a car, when there are very specific time constraints on processors executing a step of an algorithm, in more like programming like we do in the internet, let's say, when you have a NoSQL database and, let's say, Rabbit, Kafka, whatever in the background. In this case, we have no idea about these timing constraints. a message, for example, a server could be completely down and that's why it's not replying, or it's taking just long, or the network is saturated. There are all these things that we need to consider. So because of these reasons, it's like the synchronous model is not really reflecting reality, but it's telling us if the only way to implement a perfect failure detector is with these constraints, that means stop trying to implement one in the real world. That's the good part of these models, or all these things that in the distributed literature sound like impossibilities or things that, okay, but why should I care about that model that is not really real, let's say? But because it's trying to tell you, you need all these constraints to implement this particular abstraction, otherwise you won't be able. So that's the gain, let's say, from learning about the synchronous model.
Yeah, so this is so interesting because a lot of the things I talk about on this podcast, I contrast the difference between theory and practice. And this is an example where theory backs you into certain realizations about how the real world works. So it's an argument in favor of theorizing about things, because you theorize about this hypothetical thing and then you say, what would it take to implement? Oh, it's impossible.
Exactly.
Yeah.
And that's something very important to understand, that most algorithms in distributed systems, I will say probably all of them, but I don't want to generalize, but they all belong to some model. Like they have what they think the real world is, like completely asynchronous, like the second one, when there are no timing guarantees between messages going from one node to the other. There are no timing guarantees in how long the node will take to execute the step of the algorithm and how long it will take to the reply to arrive to the original node. So that's like the main difference. Again, this doesn't really reflect the real world, because in the real world, we have timing constraints. If you are going to a website and it will infinitely be loading, you will probably close the browser. And that's the same for a web service. Like now, everybody talks about microservices. If some of the microservices is not really responding, then you will consider that it's a timeout, and send a reply back to the client, database unavailable, or whatever it is you do. So we work mostly in a semi-synchronous world, in the sense of we don't know when replies will arrive, but we put constraints in time saying, okay, I'm willing to wait till a minute or whatever. So that's where the semi-synchronous model came. The point is, all the algorithms, they are either in one of these models. So you need to be really sure what you're getting into, or what, like as I mentioned, the FLP impossibility applies to one of these models, not all of them.
Engineers are always looking to simplify. To simplify testing and deployment, engineers turn to CodeShip. CodeShip is continuous integration and delivery as a service. With CodeShip, your tests are executed against your code automatically whenever you push to GitHub or Bitbucket. On Software Engineering Daily, we've done several shows about DevOps, and continuous deployment is key to DevOps. It's a great way to break down the wall of confusion between development and operations. Managing your own testing infrastructure is painful. That's why you want a service like CodeShip to do it for you. If you have a huge number of tests, you can use CodeShip's Parallel CI to run all your tests in parallel. CodeShip will spin up containers on their own infrastructure to run your tests in parallel. If the code passes your tests, CodeShip will deploy it automatically to your users. Companies like Product Hunt are already using CodeShip to speed up and simplify development. To sign up for free and start shipping today, go to codeship.com. Or to try out CodeShip's new Docker platform, go to codeship.com/Docker. So we wouldn't be talking about distributed systems if we didn't talk about failures. What are the different failure modes of a distributed system? For people who are listening who are new to the field of distributed systems, why is the idea of failure and failure detection and fault tolerance, why are these different things so important?
So depending on the failure mode that is tolerated by the particular algorithm, is what you should expect from the like what guarantees you get out of this particular algorithm. I don't know like the exact details right now out of my mind, but for example, I think Raft is an algorithm that will tell you that it only supports crash stop failures. I don't remember exactly, or if it's crash recovery. Sorry for the imprecision. But basically, in a crash stop failure, it means that in this particular algorithm, a process, when it crashed, it's completely gone. It's not going to execute any more steps wrongly, let's say, like corrupt the database, corrupt the state, give bad replies or anything. When, let's say, there is an exception, the algorithm crashes. End of story. So in the crash recovery, the process may crash and they can come back again, let's say, from a state that was saved to the file system, for example. In a crash stop model, there are the algorithm where processes come back, but because we are talking about crash stop, they are considered to be new processes, not the same one, because let's say they don't recover state. Or sometimes when you have groups of processes, they can be dynamic or static. In a static group of processes, when they crash, they are not coming back because they are static. It's not like in a dynamic model where they will be back, for example, or new ones will join the system or whatever. Anyway.
So, this idea of crash stop versus maybe partial failures, I mean, this has come up in other conversations I've had on this show. I did an interview with Fanjin Wang, who designed the Druid distributed database, and he said that the worst type of failure is actually a partial failure, where your system slows down and it's somewhat non-deterministic why that has happened. And I think that is what you're describing in contrast to the full stop crash failure. Is that accurate?
I'm not exactly sure what the other person meant by partial failure, but in the crash stop system, you are assured that the fail node is not intervening anymore in the system, let's say. So you have that assurance. And that node is considered down, let's say, by a failure detector or whatever. End of story. We don't need to contact it anymore. If we are going to vote to do leader election, let's say, that node doesn't participate anymore.
Is that one of the advantages of Erlang, where Erlang will be like really insistent about if something fails, like you kill the process?
I don't think it's related.
Oh, that's totally unrelated.
In Erlang, you could implement any of these things. I'm not sure is related, because you can have a process that crashes and comes back, then it's probably doing crash recovery. I mean, for example, in the case of omission faults, which is the third one, like we have crash stop, crash recovery, then omission faults. There, the process is omitting to do certain things, like receiving messages, for example, or replying messages. So you can have a process that is not replying to the other peers in the network, in the system, but is receiving all the requests. So, for example, if you have a cache, this process that is having omission faults in the reply case, it still is up to date because it received all the requests. So you could argue that you can have, as a client, you could ask for the state of the system, and because this process is only omitting replies to the other nodes, but it's not omitting the receiving request, is up to date. So it could reply exactly what the current state of the system is, even though it's not replying to the other nodes in the system. So you could have this in Erlang, for example.
Right.
It's not related to what you use as a programming model or system. It's more about what we have this failure, what happens with the algorithm? Will it keep doing progress or will it stop That's the thing. And for example, in the arbitrary failure mode, the Byzantine is equals Byzantine.
Byzantine faults.
Byzantine. Thanks. I never know how to pronounce this in English. So in the Byzantine faults, everything can happen here in the distributed system. Like nodes can omit replies. They can actually take all the requests and reply to all of them, but don't really persist state to the file system, for example. You could have an intruder in the system that is like, it's usually called an adversary, that is assuming that everything is correct, but it's actually logging what is happening on the system to a third party, for example. There are many things that can happen in a Byzantine failure. And each of these systems have the particularity of how many, each of these failure modes specify how many surviving nodes you need in order to keep doing progress. So if you have a crash top system, I think with a majority, I'm not entirely sure, but I think with a majority is enough to keep progressing in the system. That's why you will have all this concept of quorums and saying out of 5 nodes, if 3 are okay, then we can keep going and so on.
Right.
But in a Byzantine kind of failure, you need way more nodes that are correct in order to make progress.
1?
Sorry?
Is it 3n plus 1?
I think that's the number. Yes.
Okay. Yeah. So we should move towards that side of the conversation, consensus and quorums and all that. But I think before we get there, maybe we should define the common trade-off in distributed systems of liveness versus safety. Could you identify these trade-offs and talk about why they are often in conflict?
So the thing with safety and liveness is actually that the algorithms, they will give you this or that guarantees in either of these two parameters, let's say. Safety would be, as the slide says, I don't know if people is following this, that safety specifies that some bad things does not happen during execution. So in an algorithm, you will know that message queues, like where the communication channels are FIFO, they are first in, first out. So this order will be respected. And if you have a system where this order cannot be assured, then this algorithm is not going to apply there. So in the safety sense, it's telling you some bad thing does not happen means we will not reorder messages, for example. So that particular algorithm, I think, for example, Raft, if the leader committed the log, this prefix of the log will be shared among all the peers. So that's for sure. So if at some point that leader crashed, that the prefix that's being committed is in all the other peers in the system. So that's a safety guarantee that you can know for sure. Like, okay, I know if data was replicated, even if it crashed, at least 2 other nodes in the system, let's say, will have it, something like that. And liveness is a way of telling you, by definition, a good things happen during execution, or in other words, the algorithm under this condition will keep doing progress. For example, some algorithm says a node will eventually deliver the message. You don't know when it will happen, but the algorithm assumes this will happen, which is also very important to understand that if you have, I don't know, the data center set on fire, or so I don't know what, then the destination process eventually delivers a message, that won't happen. So, there are these liveness things that tell you when the algorithm will make progress.
Right. Okay. So to summarize these, you describe safety as, quote, communication links should not invent messages out of thin air. And then you describe liveness as, quote, a destination process eventually delivers the message. So, we should get into talking about FLP, which is Fisher Lynch Patterson. It's this important paper. It's called Impossibility of Distributed Consensus with One Faulty Process. Why is this paper so important?
So I think this paper is from 1985, when all the research on distributed system was kind of growing, and they were trying to, like, for example, do different kind of consensus algorithms, and there are different kind of failure modes and whatnot. And what this paper came to prove that before was kind of suspicion, but not really proof, that if you have one faulty process in an asynchronous system, then you cannot have consensus. Why is important? Because if some researcher at that time or even today is trying to solve consensus for a distributed system in an asynchronous model, that won't be solvable. But there were people, not because they are not smart or anything, no, it was the status of research back then. Some people were trying to solve the problem. It's like, I don't know, somebody comes and say, look, that mathematical problem has no solution, and here's the proof that you will not be able to solve it. Then all the other person that were trying to solve it, okay, thanks. But it's not that they were doing something wrong, let's say. They just didn't have a proof that it was not solvable, right? And this FLP is the same. They managed to prove that this consensus with one faulty process in an asynchronous system is not doable or solvable. So many other researchers kind of moved on and stopped investing resources in coming up with algorithms that at the end of the day will not work. And
so it's important because they saved a lot of researcher time.
And I think it's a very fundamental result in this sense, because consensus is everywhere in distributed systems. Because at some point you need to agree about the order of messages, about committing a transaction. So maybe people were not really trying to solve consensus per se, but they were trying to implement a database that will survive the data center being set on fire, let's say, whatever. I mean, this sounds like not like hypothetical cases, but back in the days, there was a lot of research related to aviation, like to how to schedule airplanes, flights, and so on, how to control planes in the air, for example. And maybe somebody needed a system that will be 100% consistent and will not give a wrong answer about the position of an airplane or I don't know, something like that.
So and go ahead.
They were trying to solve this problem, and by implementing a database, a system that will take care of solving that thingy, to not kill people, actually, because the aviation is very crucial in our daily lives, I mean, in this world. And with this paper, you could say, sorry, but that problem you're trying to solve won't be solvable. You need to find a way to go around it, or put safety measures here and there, because in this direction you're trying to go, you will not reach to a solution. That's what is important, besides saving researcher time, let's say.
Right. Okay. So there are actual, I mean, I get it, there are actual conclusions. But so if we have one faulty process in a system, can we make any guarantees about safety or liveness?
I think this is very interesting because it's another paper by an author called Marcos Aguilera. Maybe in English you say Aguilera, but I think in Spanish will be Aguilera. And he mentioned that there is a lot of confusion around impossibility results in distributed systems. Because in this FLP paper, first of all, they are talking about a completely asynchronous system, right? So we don't have timeout, for example, which means we don't have failure detectors. So it's an impossibility in the sense, like, if I tell you there is no greater number than 2, for example, in the integers. And you will tell me, well, okay, you probably should go and get some math lesson again, right? But if I tell you, wait, I'm just talking about the set of integers 1 and 2. There is no greater number than 2. Then, okay, under those constraints, I'm right? And this is what the FLP is kind of doing. It's putting a lot of constraints on the system. For example, they say, we assume that the message system is reliable. It delivers all messages correctly and exactly once. Yeah, right? I mean, in the real world, it's probably not like that. But even with all these constraints, like messages are delivered exactly once and there is no reordering and whatnot, you won't be able to solve it. Unless you later introduce timeouts, like with failure detectors were introduced to solve this problem, for example, and to actually have consensus. Because today we know there is Paxos, there is Raft, there is Zav from Zookeeper. There are many consensus algorithms which are used in the industry. So it's not like you cannot solve the problem. What they are saying is under these conditions from the paper, if you have an asynchronous model, Aguilera explains that you may have a scheduling of processors, which is very unfair. So it can happen, what I think is they prove in the paper, that a processor is never scheduled, so it will never do progress. But he say even in the real world, maybe really you have to have really bad luck for this to happen to you.
Okay,
but if you need an algorithm to be for sure proven to work, because at the end of the day, if you have an airplane, let's say you want to know that you are not going to kill people, you need to have a proof that it will work. And with FLP, they're telling you, no. They can happen that you are really unlucky and the stars are pointing in the wrong direction, and you will have this wrong scheduling, and it will fail. So it's kind of in that direction going, not in the direction of this is not possible. Is under all these constraints, it's not possible, but later people came with failure detectors and so on, so problem solved, let's say.
Okay, so let's zoom out a little bit, because I mean, we're talking about distributed consensus. We're talking about impossibility of distributed consensus with one faulty process, and I'm sure there are people listening right now who they've been paying close, patient attention, and they're like, I don't understand distributed systems. What is this thing they're talking about called consensus? So maybe we should zoom out a bit. What is distributed consensus and why is it so important? Perhaps I approached this in the incorrect order, but we should cover that topic a little bit.
So consensus is a problem of agreeing. It's an agreement problem, basically. Like, should we commit a transaction, for example? Like you meet with your friends at the train station and the train just stops. You don't see your friend. The gates are opened. The train is departing. And should I get in or not? Where are they? Maybe your friend get inside the train and you also get inside the train. You don't see them. You go out. While you were out, your friend didn't come out, but then they come out. And then, it can happen all this timing problem that we don't know what the other person is going to decide, let's say. This is kind of what happened in distributed systems. Are you ready to commit this data to the file system? Yes? No? I just crashed. Did the other processor crash? I mean, there are all these kind of questions that consensus algorithms are trying to solve, depending on the model and whatnot, is how many processes can fail, blah, blah, blah. But all these agreement problems, like, for example, the order of messages. Sometimes you really need that messages are delivered in certain particular order and applied to a system in that order, like what Kafka call log shipping or what SAB is doing, the Zookeeper algorithm or Raft. You need to know you have for example, a state machine that is applying operations. And it needs to apply them in one specific order. So to do that in a distributed system, you need to agree, because the network, for example, can have delays. So maybe my processor, my computer received all 5 transactions so far, 5 requests so far, but the computer on the other room only received 3 of them. And which are them? Did they arrive in order or not, and so on? The consensus algorithm will try to ensure that when we commit, let's say, one operation, we all commit, let's say, the first one, then the second one, then the third one, and so on. So it's mostly agreement, how to agree that we should do something or not.
Got it. Yeah, and so the properties of consensus are termination, validity, agreement, and uniform agreement. When you've been learning about distributed systems, were either of these properties particularly hard for you to understand?
I think if you go to the books that present them, they are not that hard. Maybe the language is too dry, could be. But for example, termination means that all the processes will eventually decide something, some value. That's it. It's like we have an election for president. Everybody has to vote. You know that by, I don't know, in my country we vote on Sundays, and let's say the polls end at 5 p.m. You know that by 5 p.m. everybody voted. That's what termination is kind of telling you. At some point, all the correct processes will reach a decision. The validity is that this value that was proposed is actually a value that was present in the system. Like I cannot vote for a candidate that was not present on the polls, for example. My vote will be null. That will happen in I don't know, in my country. That's how the elections work, for example. And agreement is that the correct processes. This cannot be put in parallel with an election, like a political election, because people don't decide the same thing most of the time. But in the agreement process, it's like if everybody, let's say, decides to commit the transaction, all the processes that are correct will have decided the same thing. So to bring the problem to a computer system, do we commit the transaction, yes or no? Those are the proposed values, which is usually in this case called binary consensus, because you have yes, no, true, false, 1, 0, or whatever. So from these two values, at some point, all the processes that are correct will decide something, that's termination, and the agreement will mean that whatever they decide, commit or don't commit, attack, don't attack, it will be the same, because otherwise we don't have consensus. I mean, we don't have an agreement.
Absolutely.
And the uniformity is specifically of uniform consensus, which is more strict because it says that processes correct or not decide the same. I'm not sure, maybe I'm wrong, but I'm not sure this applies to real system. I think it is more a theoretical thingy, but I'm not 100% sure.
Okay. So in your blog post, you wrote about the concept of time, and you said that the idea of simultaneity is something we have to let go. What do you mean by that?
This is actually even a very interesting philosophical topic, but it's if you just think about physics, like what I'm seeing right now, for example, my computer screen.
Relativity.
Exactly. It's not really what is happening right now, whatever now means. The light had to travel from my screen to my eyes, process my brain, etc. So what does it really mean to be simultaneous? So if you have a network, electrons will have to travel through the network. They will have to reach the, I don't know, CPU, whatever, RAM, and until we have the actual value that the other processor shared, for example. So what is simultaneity? From the point that, let's say we have an abstraction that sends messages, like in Erlang, process ID, send, and some message. From the moment that this was executed, the information is actually old, right? we kind of try to put steps there and add some kind of time concept because we are used to this kind of thinking, but actually it's not what is happening in the real world. Therefore, in distributed systems, there are like time as it is, like clock time is not really used for measuring things because what does it really mean? Like you need to have like atomic.
We use vector clocks,
for example, or logical clocks, or like you need a way to tell this thing is older than this other one or happened before, as they said, but you cannot use like, let's say, human time. I don't know how to call it, wall clock time. You cannot use that because this means that you have a way to synchronize in CPUs with atomic clocks probably, and like Justin Sheehy discusses in his paper or article for the ACMQ. And who has that? Who has access to a system like that?
Yeah.
Mostly if you're running, I don't know, an EC2 or whatever, you won't have probably synchronized clocks, or most of the time they will be synchronized. And because of that, you need a way to tell what happened after what happened before, and then you have all these kind of logical clocks, like these vector clocks or the Lamport one, which are just, I think, an increasing integer. But at least you have a way to tag requests and say this one happened before than this other one.
Right. So we have covered a ton of distributed systems topics, and there's many more we could have covered, but the time draws near to close off. So, I'm not sure. Hopefully there's still people listening. I feel like there are, it's like there's two audiences. There's like total novice people who have no idea of what a distributed system is, and then there's really experienced distributed systems people. And both of these people have probably dropped off by now, so we're left with like the intermediate distributed systems people. So I don't know, or maybe there's people of the other two sides of the bell curve who are still listening. But in any case, what are the most important lessons to take away from this discussion? I mean, should people be thinking about the actual topics that we were discussing, or is there some meta lesson about distributed systems and learning about distributed systems that people should be taking away?
For me, like lesson 0, let's say, is each area of science has its own jargon. And you need to know that to understand what they are saying. I think the asynchronous versus synchronous is one great example here. Like consistency, we probably don't have time to go there, but there are many meanings of the word consistency. It's just like cup theorem consistency versus acid consistency. They are different things. So how are we going to understand what the cup theorem means if we come, let's say, from an acid point of view of databases? Trying to understand consistency from there, we are going to fail because we started with the wrong foot, let's say. So for me, that's very important. Learn at least the basic concepts. You don't need to know all the failure modes and quorums, numbers, and whatnot, because you probably don't care about that in real life. You need to know that at some point an algorithm will give you some guarantees related to that, and you need to understand what it means to you. But I think the other lesson is that from understanding this theory, not too deep, because as I say in my blog post, we don't have forever to learn. We have lives to follow as well. It's quite difficult to understand trade-off of different distributed systems, like I was mentioning before in the case of queues or databases, like Kyle is explaining on his blog. If we don't know all these things that could be implemented or what it means to be eventually consistent, it happened a lot that people wanted, like, eventual consistency is cool, I just read it on Hacker News, but then I need to implement a system that doesn't allow duplicates. Okay, but then how are you going to conciliate that? Like as I said before, this message queue doesn't have any synchronizer. All the nodes are symmetric. They all have the same power, let's say. Okay, but then they will send you duplicate probably. You know what I mean? So getting to the point where we understand what it means, what they are offering us. For me, that's the important lesson. Or, okay, Raft is really cool. Everybody talks about Raft, but then maybe I need a system where I need Byzantine fault tolerance. Oh, then maybe Raft is not the way to go.
Yeah.
You know? So I will take it from a problem point of view, and from there get into what I probably need to learn. But I won't go, let's say, somebody told me read about FLP, because as I think I've been saying through the whole podcast, you will grab the paper, read asynchronous, it won't mean what you think it means, and then the rest of the paper is meaningless, let's say.
So perhaps the takeaway is figure out what you're building or what application, what is your end goal, and then you'll have a natural motivation to learn the theoretical necessities that supply you with the knowledge to fulfill that goal. That's great.
And if you will dig into the literature, know about the models. Like these 3-time models are essential to actually pick the right paper, because probably won't be the one you are looking for.
Yeah. That's great. Well, Alvaro Videla, thanks for coming on to Software Engineering Daily. It's been really intriguing talking to you about distributed systems. It's been a real trip back into my my time in school and my academic distributed systems courses.
No, thanks for having me. I mean, for me, it's really, really cool topic to discuss, to see different point of views and so on.
Absolutely.